We have completed the finite element method for analysis of trusses. Truss problems we have finished. Bar problems also we have finished. Today let us take up finite element method for solving beam problems. That same procedure what we have already discussed in truss for beams also let us follow. First let us derive the stiffness matrix or element property for the beam. That step 1, consider a prismatic or non-prismatic also it can be used. Generally it is applicable for both prismatic as well as non-prismatic test. Consider a beam element of length L and flexural rigidity EI in global and natural coordinate system. As below. You consider a beam element 1, 2 in global coordinate system. This is x, this is y, and here it is x is equal to x1, x is equal to x2, the global coordinates, length L and flexural rigidity EI. So any point coordinate is x and this time the displacement u or u at any point. This is the global coordinate system. Beam element in global coordinate system. In natural coordinate system, the same element it is represented in this fashion. The origin is taken at the center like this, and it is z coordinate. Here z is equal to -1, z is equal to +1, z is equal to 0. This is the beam element in natural coordinate system. Natural coordinate system. The representation of the beam element both in global and natural coordinate system are like this. Usually we will determine the element property, that is the stiffness matrix, only in the natural coordinate system because it is easy for deriving the stiffness matrix. So with this particular thing, given data, so first assume the element to be isoparametric type. Isoparametric. So if you just take that as isoparametric type of element, then the natural coordinate at any point, that is a global coordinate at any point, is given by n1 x1 plus n2 x2 for isometric type. There n1 is equal to 1 minus psi by 2 and n2 is 1 plus psi by 2. This already we have derived the shape functions where n1 and 2 are the shape functions. or the shape functions of this beam element. Same shape function. Then Jacobian matrix, that is the matrix which transforms the element coordinates from the natural coordinate system to global coordinate system. It is for one dimensional thing. It is given by delta x by delta psi. That is the Jacobian matrix. So x is equal to n1 x1 plus n2 x2. So this is nothing but delta n1 by delta psi into x1 plus delta n2 by delta psi into x2. Delta n1 by delta psi is nothing but minus half. Similarly, delta n2 by delta is plus half. So therefore, Jacobian matrix is equal to minus half plus half into minus half into x1, that is x1 by 2 plus this is x2 by 2, that is nothing but x2 minus x1 divided by 2. This is nothing but L by 2. So Jacobian matrix is just equal to L by 2 or Jacobian inverse. Inverse of Jacobian matrix is nothing but delta psi by delta x, which is equal to 2 by n. So this much information first you should have. Then next, let us consider the beam element, the number of degrees of freedom at each node is 2. So vertical displacement and rotation at each node. These are the nodal degrees of freedom, E2, theta 2. So this is nodal degrees of freedom for the element, and the nodal coordinates we will call it as Q1, Q2, that I have written not Q1, Q2, it is V1, theta 1, V2, theta 2. This is the nodal degrees of freedom. Nodal degrees of freedom of the element. This also we know. Now, we know the displacement at any point V and theta. At any point, the displacements or in the beam element can be represented like this. V you can represent it as in the polynomial form. V is equal to alpha 1 plus alpha 2 psi plus alpha 3 psi square plus alpha 4 psi cube. In the polynomial form, that also you know, the displacement model, V you can represent it in this polynomial form because it's a function of z in the natural coordinate system. The displacement we can represent it in this fashion, or in matrix form, you can write it as V is equal to 1 psi square psi cube raised to alpha 1, alpha 2, alpha 3, alpha 4. So this is the equation 1. That is the degree of freedom V at any point You can represent it in the polynomial form like this. Then similarly, theta is nothing but delta V by delta x, the global coordinates. Rate of change of the vertical displacement is slope. So this is nothing but Jacobian inverse, that is, I can write it as delta V by delta xi into delta z by delta x. This delta z by delta x is nothing but Jacobian inverse, which I have already derived. So this is nothing but Jacobian inverse into delta V by delta z. Jacobian inverse is 2 by L, or theta you can write it as 2 by L into delta V by delta z. V you have represented like that. So this now you can differentiate partially with respect to z. You will get this Jacobian inverse is 2 by L. So into this will be partial differential coefficient of 1 is 0, partial differential coefficient of z is 1, 2 z squared is 2 z, this will be 3 z squared into alpha 1, alpha 2, alpha 3, alpha 6. This is your equation 2. The displacement, vertical displacement at any point and corresponding slope at any other point that you are getting in this equation. Now we have to determine this alpha 1, alpha 2, alpha 3, alpha 4. For that, we have to, from the first principle, which we explained in finite element method of analysis, while discussing displacement models, you apply this equation 1 and 2 to the node 1 and 2. At node 1, you know, psi is equal to -1, v is equal to v1, theta is equal to theta 1. Similarly, at node 2, z is equal to +1 and v is equal to v2, theta is equal to theta 2. You substitute this condition in equation 1 and 2, you will get 4 equations, and that 4 equations you can solve, or you find the inverse matrix and get the coefficients of alpha 1, alpha 2, alpha 3. So now we know at node 1, at node 1, z is equal to -1, v is equal to v1, and theta is equal to theta 1. Also, at node 2, z is equal to +1, that already you know here, z is equal to +1, I have represented, and v is equal to v2, and theta is equal to theta 2. There are the 2 degrees of freedom I have mentioned in this figure. So substituting this condition, this boundary conditions in 1 and 2, in equations 1 and 2, E and theta, in equations 1 and 2, this is the theta. So when equations 1 and 2, we get like this. So at node 1, V is equal to V1. I will write it in the matrix form right away. Like this. Alpha 1, alpha 2, alpha 3, alpha 4. So at node 1, V is equal to V1. I am applying the equation 1. At node 1, V is equal to V1, Z is equal to -1. If you substitute Z equal to -1 in this equation 1, you will get here the coefficients 1 and z is equal to minus 1, z square is minus 1 whole square, that will be 1, z cube is minus 1 whole cube, that is minus 1. So 1 minus 1, 1 minus 1 will be that first condition. At z equals minus 1, e is equal to alpha 1 minus alpha 2 plus alpha 3 minus alpha 4. That's what you are going to get. Then, if you just apply same node for second equation, theta is equal to theta 1 and z is equal to minus 1. So if you substitute z is equal to minus 1 and theta equals theta 1, you will get theta 1 equals 2 by L into 0. So this will be 0, 2 by L into 1. So this is 2 by L. Then 2 by L into 2 psi, that is z is equal to minus 1. So it is 2 into minus 1, that is minus 2 into 2 is minus 4 by L. Then 3 psi square, z is equal to minus 1 square plus 1 into 3 into 2 by L, it is 6 by L into this alpha 1 alpha 2 alpha 3. This is by applying this condition. V at node 1, z equals minus 1 and v equals v1, theta equals theta 1. In these two equations, if you substitute this entire condition, you will get this first two rows. Then if you apply the second condition at node 2, z equal to plus 1, v is equal to v2 and v2. I have to put psi is equal to plus 1. On same lines, you will get 1, 1, 1, 1. 1, z is equal to 1. Z equals 1 square, that is 1, z cube, 1 you will get. Then at theta is equal to theta 2 here. It is 2 by L into 1. The first one is 0. 2 by L into 1, 2 by L. Here 2 by L into 2, that is 4 by L plus 4 by L. It is here it is 6 by 3 into z equals 1, so 3 into 2, 6 by L. So this is the equation you are going to get. So if you put these two conditions, that's the boundary conditions, at node 1, z is equal to minus 1 and v is equal to v1, theta equals theta 1, you will get this first row. In these two equations, if you substitute. Similarly, other conditions, if you substitute, you will get the two. In the matrix form, it is easy for substitution. Now, therefore, now you can either solve this equation for alpha 1, alpha 2, alpha 3, alpha 4. So there are 4 equations, 4 unknown constants in terms of nodal displacement u1, v1, u2, v2, you can find out. So either you can solve or you can find the inverse. So therefore, you can say alpha 1, alpha 2, alpha 3, alpha 4 is nothing but inverse of this matrix. 1, 0, 1, 0, this one. Theta 1 is 0, okay, 1, 0, 1, 0. Then minus 1, 2 by L, 1, 2 by L. Then 1 minus 4 by L, 1, 4 by L. Then minus 1, 6 by L, 1, 6 by L. Inverse u1, now v1, theta 1, v2, theta 2. So this is inverse of this matrix into that. So if you inverse this matrix, you will get this particular thing. I don't do it straight away, you can remember, I will give you a particular value. So if you invert this, you will get this. Either inversion or by normal solution of simultaneous equation, you can just do it. If you do it, you will get this. Here you will get 2 minus 3, then 0, 1, L by 2. Instead of 2 by L, you will get L by 2, L by 2, then minus L by 2, minus L by 2, then L by 2. Then you will have 2, 3, 0, minus 1, then minus L by 2, minus L by 2, then L by 2, L by 2. This is the inverse of this particular matrix. And of course, this E1, theta 1, E2, theta. This is what? This is alpha 1, alpha 2, alpha 3, alpha 4. Now you substitute this alpha 1, alpha 2, alpha 3, alpha 4. You will get the value of V1, V2 in this equation. Substituting for alpha 1, alpha 2, alpha 3, alpha 4 in 1 and 2. You will get the equations for the displacement V or theta at any point in the beam element. So substituting the values of alpha 1, alpha 2, alpha 3 and alpha 4 in 1 and 2. This is equation 1, this is equation 2. In 1 and 2, if you substitute, you will get E is equal to 1 sine V equals 1 sine psi square psi cube into alpha 1, alpha 2, alpha 3, alpha 4, which is nothing but this 1 by 4, 1 by 4 into that matrix. 2 minus 3, 1, 0, 1, then L by 2, minus L by 2, minus L by 2, L by 2, then 2, 3, minus 0, minus 1, then minus L by 2, minus L by 2, L by 2, L by 2. That is the inverse of that particular matrix multiplied by the nodal degrees of freedom V1, theta 1, V2, theta 2. This is that. I just substituted that alpha 1, alpha 2, alpha 3, alpha 4 here. So or you will get E is equal to, this is 1 by 4 matrix, this is 4 by 4 matrix. If you multiply, you will get a 1 by 4 matrix, that is V is equal to 1 by 4. I will keep this 1 by 4 as it is. Then 1 into 2 minus 3 into psi square into 0, psi cube into 1. So that is nothing but 2 minus 3 psi, 2 minus 3 psi plus psi cube. First one. Then second one, L by 2 into 1 L by 2 into 1, 1 minus L by 2 into 0, psi, L by 2 I have taken outside, so it will be 1 minus psi, then this is minus psi square, then this is psi cube. This is second one, then next you have 1 by 4 already have taken outside, you have 1 into 2, 2, 3 into psi, 3 psi, then psi square into 0, 0, psi cube into minus 1. You will get 2 plus 3 psi minus psi cube. And lastly, this will be L by 2, this will be L by 2 into 2 plus 3 psi, or not 2 plus 3 psi, is 2 into minus 1, then psi minus 1, minus psi, minus plus psi square, plus psi cube. Into, of course, that nodal dispersions, V1, theta 1, V2, theta. This is, you call this as equation 1, 2, 3. This is the third equation. This is the actual equation for displacement, vertical displacement at any point in the element. Similarly, slope at any point is given by substituting these values of alpha 1, alpha 2, alpha 3, alpha 4 in equation 2. You will get this is nothing but 2 by L into this 0, 1, 2 psi, 3 psi square into that 1 by 4 into that same matrix 2 minus 3, not 2 minus 3, yes, 2 minus 3, 0, 1, then L by 2, minus L by 2, then minus L by 2, L by 2, and 2, 3, 0, minus 1, then minus L by 2, minus L by 2, L by 2, L by 2, into E1, theta 1, E2, theta. So this again, you can multiply, this is 1 by 4, this is 4 by 4, the result will be 1 by 4 matrix. So theta at any point slope is given by theta is equal to 1 by 2 L, that is 2 by L, L by 2. Okay. This is 2 by L into this, if you multiply 0 into 2, 0, then this 2 by L, 1 by 4. If you take, so this will be 1 by 2L. 1 by 2L. 2 by L and this 1 by 4. If you simplify, you will get 1 by 2L into, this is 0 into 2, 0. This is 1 into minus 3. It is minus 3. This is 0. This is 3 psi square. So 3 psi square minus 3. Or if you take 3 outside, 3 psi square 1 minus psi square. 3 to 1 minus psi square. Or minus 1 less psi square. Psi square minus 1. 3 psi square into 1. 3 psi square, this minus 3. Okay, this is 0, this is also 0. So you will get 3 into 1 minus, the minus 1 plus x square, then second row, L by 2, I will take it outside. You will get L by 2. This is L by 2 if I take outside. And that L by 2 and this L, it will cancel. So you will, that L by 2, you will keep it as L by 2 into minus 1. 0 into this 1 into minus 1. Minus 1. Then 2 into minus 2 xi. That is minus 2 xi. Minus 1 minus 2 xi. Then this 3 xi square plus 3 xi square. 3 xi square. 3 xi square. Okay. Similarly, next element 0 into 0, 0. This is 3 into 1, 3. This is 0. This is 3 xi square. 3 xi square plus 3. So I will take 3 outside. I will get 3 into 1 plus xi square. Here you will get 3 into minus 1 xi square. Here you will get 3 into 1 plus xi square. Next. 3 into, this is minus 1, minus xi square. This is minus 1 plus xi square. This is minus 1. 1 you will get, that is 2 xi, 3, 1 into 3, then minus xi square, 3 xi square. 1 into 3 xi square into minus 1. This 0 you will get, this also 0. First and third will go. Only this will complete. Then lastly, this is L by 2 into, you will get minus 1 plus 2 xi plus 2 xi plus minus 3 xi square. Minus 3, 0. Then minus 1, you get it, 2 will cancel. You will have L by 2, have already taken outside. So that L by 2 is this, minus 3, 2 xi, minus 3 xi square. You will get this completely into V1, theta 1, V2, theta 2. This you can call equation 4. So I have obtained expression for the displacement V by equation 3 and displacement theta. These are the shape functions now. I have derived the shape function for wheel element. So shape function after all for one dimensional element Q is equal to N1 Q1 N2 Q2. But here it is 4 shape functions, and these shape functions we call Finite shape functions, because slope is also involved. That is, first derivative of displacement is also coming into picture. That's why it is called, this shape function is called Finite shape function. So therefore, we can write it as H1. This entire thing I will call it as H1. This I will call it as H2. This I will call it as H3, H4, shape function. So V is equal to 1 by 4. That 1 by 4 is there. I will keep it as it is, into H1 plus L by 2. L by 2 is there, into H2 plus H3 plus L by 2 into H4. L by 2 into H4. So this is that, and of course, into this I can call it as Q, the element, nodal displacement of the element. QE is nothing but V1 theta 1, V2 theta 2. the displacements at the two ends is that. So where QE is nothing but V1, theta 1, V2, theta 2, into 4 by 1. And of course, theta is equal to, theta is come to where QE is equal to that, and H1 is equal to 2 minus 3 xi 1 by 4 into 2 minus 3 xi plus Q. Or I will keep that as it is. 1 by 4, that is their common. And H2 is equal to 1 minus xi minus x square plus Q. And H3 is equal to 2 plus 3 xi plus minus Q. 2 plus 3 xi minus Q. And H4 is nothing but minus 1 minus xi plus x square plus Q. These are called shape functions. Finite shape functions. Finite shape functions. Finite shape functions for D-element. It gives the displacement at any point, vertical displacement at any point of the D-element. This much exercise you have to do before obtaining the stiffness matrix for D-element. You have to do this much exercise. Then you can find theta also on same lines. So theta you can write it as also this shape function is the displacement A, which gives the displacement at any point or 3. Either one you can use it. A and 3 they are one and the same. Only here I am representing these as H1, these as H2, these as H3, H4. That's all, nothing other than that. And theta is given by differential coefficient of this delta E by delta X, which is nothing but this 1 over 2L into, I will write it in brackets, 1 over 2L into 3 into z square minus 1 or minus 1 z square plus L by 2 into minus, the same thing you can write it, minus 1, not minus 1, 1 minus z square minus z cube minus 1 minus L by 2, 1 minus 2z, L by 2 minus 1 minus 2z plus 3z square plus 3z square, then plus 3 into z, 3z, L into 3z, 3 into 3z plus 1 minus z square. Here z square minus 1, there is 1 minus z square. Then L by 2 into minus 1 plus 2z minus 3z square. This multiplied by QE. Instead of this, V1 theta 1, V2 theta 2, I am writing it as QE. So this is that equation. You call this as B. These equations you have to remember for solving any beam problem for the slope and deflection at any point of the beam element are given by these equations. So knowing V and theta, slope and deflection, you can find the moment. So moment, bending moment at any point, M is given by EI E2V by dx square. The second derivative. So this theta is nothing but dv by dx. That you know from that equation B. This is equation B I told. This is equation A, equation B. So this equation B you can differentiate with respect to x again twice. Either B you can differentiate twice or theta you can differentiate once. So you know, as said before, this is a function of z. So then once this has to be, but we have to differentiate with respect to global, so we have to use again Jacobian. So this we have to multiply by again 2 by L into 1 by 2L. That is nothing but VI into d by dx of theta delta theta by delta x. So that is nothing but VI into 2 by L, that is Jacobian inverse, multiplied by 1 by 2L, here 1 by 2L into this. I have to differentiate partially with respect to z. This if you differentiate, you will get 3 into 2z, that is 6z. 3 into 2z, and minus 3 partial differential equation is 0. So that you need not have to bother, that will go. Then this is L by 2 into this is going to take partially, this will be 0, this will be minus 2, L by 2 minus 2, this will be 6z plus 6z minus 2 plus 6z. That is second one. Next here it is 3 into minus 2z, that is minus 6z. Then L by 2 into this, it will be 2 minus 6z. 2 minus 6z. And of course, element nodal degree of freedom. So this partially are differentiated with respect to x theta. When we are differentiating this partially with respect to x, then I have to use Jacobian inverse into the differential, partial differential coefficient with respect to z. We can do that with respect to z. So our m, we can write it as this 2 will go, this will be vi by L square into vi by L square, correct, into 6i. Here I can take 2 outside, that 2 and this 2, it will cancel. We will have L into, this will be 3i minus 1. I will take 2 outside. I will get 2 into L by 2, that will be L. Here 2 I have taken outside, it is minus 1, here 3 sides, 2 I have taken outside. Then here it is minus 6L. Then this is same thing, 2 I will take outside, I will get L into 1 minus 3 psi. Here it is 3 psi minus 1. Here it is 1 minus 3 psi. Into this is the moment equation. See, this is the moment equation at any point. So this is moment deflection at any point, vertical displacement. This is slope at any point. This is moment at any point in the beam. Similarly, we can get shear force at any point. And this is actually the difference between finite element method and your conventional method of analysis, other one, what we have done. Here, we are getting directly the equations for slope, moment, and shear ability. So only unknowns are these two, V and theta. And once V and theta are determined, the moment and shear automatically will be done, and that will not be determined actually as we have analyzed in the conventional method. This is the basic difference between finite element method and the only thing is to remember these equations. This equation for reflection in terms of Hermite shape functions, the equation for slope, which is nothing but first partial derivative of the deflection, and moment, which is nothing but second partial derivative of deflection or first partial derivative of slope, and then shear force at any point is given by del V. That is nothing but delta M by delta X. Again, we have to differentiate partially with respect to global coordinate system. This is actually the definition. V equals rate of change of moment. Then moment is nothing but rate of change of slope. Slope is nothing but rate of change of displacement. Displacement actually you have to derive from first principle of the finite element method. Assume it in polynomial form, get it. So this much procedure is there. Finally, you have to remember these things. And V is nothing but delta M by delta X. Again, this M is function of Z. We are differentiating with respect to X. So we have to apply, multiply this by Jacobian inverse. That is the transformation matrix which I told for isokinetic elements. So this again, I have to multiply by 2 by L into ER by L square into partial differentiation of with this particular expression with respect to Z instead of X, we can do with respect to Z. Now, since I am multiplying by Jacobian inverse, here also I multiply by Jacobian inverse of that expression 1 over 2L. So that you have to be careful. You have to multiply by that Jacobian inverse. This you have to remember, because we are treating all these elements as isoparametric element. So here by L square, here this sig sign partially we are differentiating with respect to Z now. It is 6. Here partially differentiating sign, so this will not be there, only it will be 3L. Here it is minus 6, here it is minus, here that is very simple, and of course the nodal displacement. That will be careful with V1 theta 1, V2 theta. That is, so for V is equal to, here I will take 3 outside, here count factor 3, so that 3 if I take outside, that 3 into 2, it will be 6 L by L cube into, this will be 2, 3 I have taken outside, this will be L minus 2, this will be minus L. 2, then 3. this, you call this as equation. So moment equation, here equation, stroke equation, and deflection equation at any point. This, if you remember, and also derivation as well as expression, you can derive the stiffness matrix for the beam element. So that we will take up next. To derive this again, like this, a bit out. To derive an expression for stiffness matrix. For the beam element. So we know from flexural formula m by I is equal to sigma by y. This is the famous flexural equation which you know. Or you can say m is equal to, not m, I will take sigma, or sigma is equal to my by I. You have the expression for m. Use this flexural formula equation and get sigma. Then once you know sigma, you can find strain. Therefore, strain at any point in the beam element is given by sigma by E. It can be elastic limit. Sigma by epsilon is nothing but E modulus of elasticity, or epsilon is sigma by E. So that is nothing but sigma is m by I. M by I is sigma E divided by, this is what was epsilon, that is strength. So substituting for m from equation C. You know from C what is m. So you will get strain epsilon is given by EI by L square. Here you have my by EI. So for m, I am substituting that entire expression. For m, this entire expression will come into y by EI. So this into y by EI. Correct? This my by EI, this EI will go, you will get just y by L square. Y by L square into y by L square into 6i L 3i minus 1 minus 6i L 1 minus 3i. Of course, that V1 theta 1 into theta 2. It is nothing but your QE. This is the expression for strain at any point, or you can call this as epsilon is equal to strain displacement matrix into QE. This you can call it as epsilon is equal to BQE, where B is equal to strain displacement matrix, strain displacement which is nothing but y by L square into 6i L into 3i minus 1 minus 6i L into 1 minus 3i. This you have to remember. Find displacement matrix B for beam element. Then we can use general formula for stiffness matrix of one-dimensional element, which I told, that is volume integral dt Cb. Using that expression, you can get the stiffness matrix of beam element. So then, let's say also we have this stiffness matrix of the element is given by the volume integral into dt dB. This already I have derived in the previous class. Show that stiffness matrix of any element is given by this. We have derived here, so we can substitute that and get the value of Kb. Therefore, Kb, that is beam element stiffness matrix, is nothing but this volume integral Bt is y by L square into that 6i and L into 3i minus 1 minus 6i L into 3i 1 minus 3i. This is the transpose. Then D is nothing but E, modulus of elasticity, because it is one-dimensional element. The constitutive matrix is E. Into B. B is again y by L squared into 6i L into 3i minus 1, 6i minus 6i L into 1 minus 3i. That is B. So Bt D into D. dV is nothing but dA into dz, because we are integrating with respect to dz, z coordinate. That's natural coordinate system. Now you watch this y into y square. So you know dA into y square. This dA into y square is nothing but moment of inertia of the beam element. So you know dA into y square is equal to this dA multiplied by y into y square. It is nothing but that dA into e into y. I can y into y. I can represent it as I and okay, this first time substitute, and of course these sides this is because we are multiplying by dB. This is in global coordinates, so this is dA into dx. Because dB is in global coordinate, so this has to be dx. And this we have to take it in terms of dz. So you know that dx is nothing but L by 2 into dz. So that is the Jacobian transformation. Because you know dx by dz is nothing but Jacobian, and Jacobian is nothing but L by 2. That I have already derived earlier. so that we can see that first, the beginning of the step, there we will get this. So therefore, therefore this KE is given by, so now this is the volume integral, it comes to line integral. Since it is y-coordinate, it is minus 1 to 1. Here you have L squared, that is L to the power of 4, and here it is L by 2 because of dx has multiplied by, replaced by d psi, I will get L by 2 into d psi I will write. And this dA square is nothing but I. So I will get into di. Then this, if you multiply 1 by 1, this is 4 by 1 matrix, this is 1 by 4, you can multiply, you will get a 4 by 4 matrix. That 4 by 4 matrix is nothing but 36 square, because 6 I into 6 I, that is 36 I square, 6 I into L into 3 psi minus 1, you will get 6L into 3 psi square minus psi, then minus 36 psi square, then 6L into 6L into 3 psi square plus, it does matrix multiplication. This into this, this into this, this into this, that is this into this, and this. So you will get each matrix multiplication 4 by 4 matrix. Then you will get, I will write only the symmetric matrix. So this is L square into 3 psi square minus 6i plus 1, that I will get minus 6L into 3 psi square, I have minus I, then L squared, 3 psi square minus 1, this is L squared to 9 psi square minus 1, minus 1, then 36 n square, then this is minus 6L into psi square plus psi 3 psi square, 3 psi square plus psi, and lost this will be L square into 9 psi square plus 6i minus 6i plus 1. That is this and this. That is this matrix, and y by L square, and this dA, E, and also dx. If you use this, you will get h into dz. So, or finally, if you differentiate or if you integrate this expression with respect to z and substitute upper and lower limits. So final expression, you will get a stiffness matrix in this fashion. So I will write that. So or is finally, if you integrate on integration, you get KE equal to, so this EI, this will be L cube, EI by L cube into, if you substitute this upper and lower limit, integral of this side is side, for that side, if you substitute upper and lower limit, you will get 1 minus or minus 1, 2, that 2 and this 2 will cancel, you will get only this to be integrated. So finally integration will result in this, then 12 and 6n minus 12, 6n then this is symmetric. The same expression will come. The second column will come as second row. This will come third. This is fourth. Like that. Similarly, this, that's symmetric. So here also it will be symmetric. You get 6n. Here you will get 4l square. This minus 6l. This will be 2l square. This is minus 6l. This is 2l square because symmetric. This is 12. This is minus 6l minus 6l 4l square. This is the final expression for stiffness matrix of a beam element. This much exercise you have to do all from using the knowledge of finite element method. First, that is Jacobian, treating it as a subparametric one. Then relationship between Jacobian and this natural and global coordinates, that's L by 2 Jacobian, L inverse, that Jacobian inverse you have to take. And finally, find an expression for V, then find an expression for theta, find an expression for moment, shear, and using that bending equation, m by I is equal to sigma by y, get sigma, then finally get the expression for strain, and that strain is nothing but BD, that strain displacement matrix. Then using that strain displacement matrix, what we have derived for general stiffness matrix equation, using this formula, you can get the stiffness matrix of the segment. All this I have explained in the finite element procedure that we are using here. Using that procedure, I have arrived at the stiffness matrix. Now I will work an example and prove this particular topic. So because my syllabus, we have only this derivation of stiffness matrices for truss and beam, and then working through problems on this application of that stiffness matrix for the practical problems. Beam problem as well as truss problem. Truss problem I have done, beam problem will do it. So you take an example, find the displacement, find the displacement under concentrated load of the beam shown here. Take this beam example. This I will take EI and again 2 meters, and you have a concentrated load which is at 1 meter from at the end, and here you can take a division of 24 millimeters. You can take it as 2 into 10 to the power of minus 6 meters to the power of You can take it as 50. You have to find the displacements. That is, the displacements are vertical deflection as well as slope. V and theta, you have to determine under this particular concentrated load point. I told you the advantage of why you have selected this problem is already in the beginning I told advantages of finite element method. It can be applicable for how complicated loading, complicated boundary conditions change in the sections. Whenever there is a change in section, everything I have taken here, this is 2EI, this is EI, change in section is there, and at some load point, concentrated load point, I have to determine the slope and deflection. Then of course, once you determine the slope and deflection, you can use that moment and shear force equation which already I have derived. So that is the basic difference between classical method and this finite element method. Here we are determining only the displacements because they are the ones which are related to shape functions, P matrix and all. So that we determine and then using that moment and shear relationship, that's equation C and D, which already I have derived, that you have to remember, and they are all in natural coordinates. Each portion element you have to treat it separately, and knowing that natural coordinate distance of any point where you have to determine the deflections, and you can substitute that value and evaluate internal forces, moment and shear. So here, first, this is the beam element. So it has number of elements. First, number of nodes, I will take it. Number of nodes. Number of nodes. Of course, there is a node here, its boundary. We have to select a node at the boundary as per our finite element method, which I just explained in the earlier classes. Always we have to select a node at boundary. This is one boundary, this is another boundary, I have to select a node there, and this is the third boundary, I have to select a node there. 3 nodes are must because they represent the boundaries of the element. There are 2 elements here, strictly speaking, 2 elements they have given. From the 2 element ends, first I have to select at the ends the nodes. Then there is a concentrated load here. So this is a surface load. Due to a surface load, I can find the equivalent nodal reactions. Because all nodes has to be acting only at the nodal points in this finite element method. All nodes and all the unknown displacements, we have to treat it only at the nodal points. Right? Because we have the equation for the nodal displacements only through the shape equations. We have to select all unknowns only at the nodal points. And here, since it is surface load acting on this complete element, I can find the equivalent loads at the 2 ends, 1 and 2 of this element. Now from this is 1 element and 2 nodes. And when we come to this element, here there is a concentrated load, and I told in the finite element method, we have to select a node under that concentrated load point as well as a moment. Suppose if a moment is given at any point, we have to select a node there also at the points where moment and concentrated loads are acting. So I have to select one more node here since there is a concentrated load 3 and about this is 4 node. So number of nodes it is 4. If there is a moment given at any point in the problem, I have to select that. If it is a surface load, due to surface load, I have just given the expression already. And while deriving the stiffness matrix, the element equation, Kd is equal to F, that I have already given, is that how to calculate the equivalent load for a surface load or body self-weight, body force. Body force, surface forces, well, we can get related through shape function and we can get the equivalent loads. But for concentrated loads and movements or any other load, we have to select a load at that point. So here, though there is no node is given, here I have to select a node, and of course in the problem they have asked find the displacements under the concentrated load. So naturally when we find out, when we select a node at that node point, we are determining the unknown displacements. So automatically that will be taken care. So number of nodes is 4 and number of elements, now it comes to 3 elements, not just 2, it will be 3 elements. Number of elements equals 3. Because in the isoparametric idealization, we have 2 varieties. One is superparametric element, subparametric element. Or isoparametric elements means number of nodes for unknown displacement as well as geometry, they are one and the same. But if number of nodes are for displacements are more than number of nodes for geometry, then it is called superparametric element. And other way, it is called subparametric element. Here it is a superparametric variety because we are selecting one more node for finding out deflection because there is a concentrated. It's a superparametric variety. In the isoparametric itself concept, we have 2 varieties. So number of nodes will be more, and that node will be taken care at the time of calculations, the degrees of freedom. So here nodes and number of degrees of freedom, total number of degrees of freedom. At each node you have 2 degrees of freedom. Here 1, 2, 3, 4, here 5, 6, then 7, 8. Number of degrees of freedom is 8. So out of these 8, only 3 are the unknowns. Here at this node 1, both these displacements are 0 because it's fixed boundary condition. We are imposing the boundary conditions. When you impose the boundary condition, here both displacement Q1 and Q2 are 0. And here Q3 is 0, whereas Q4 is there, that is the unknown. This is Q4. This Q4 we have to determine. Here it is Q5, Q6, both we have to determine. In the problem also we have to find the displacement under the load point. So both Q5, Q6 we have to determine, Q4 also we have to determine, but this Q7 and Q9 they are 0. So therefore nodal degrees of freedom are this Q1, Q2, Q3, Q4, Q5, Q6, and 3, 4, 5, 6, 7, 8, Q6, Q7, Q8. This is that nodal degrees of freedom Q, that is for the element. QE is Q1 to Q8. There are 8 degrees of freedom. And kinematic indeterminacy is only 3. That is unknown displacements. Unknown displacements. That is your Q4, Q5, Q6. These are their known displacements. Because by boundary conditions, Q1, Q2, Q3, Q7, Q8 are 0. Q1, Q2, boundary conditions. Boundary conditions. That is the essential boundary conditions is called. Essential displacement, that is displacements are zero. The vertical displacement as well as first derivative. But second and third derivative I am not equating it to zero. They are called natural boundary conditions. That's implied here. M and B equation we have to get. We can determine at any point using that equations B and C. Using essential boundary condition. So this is related to the unknown displacements B and theta. That's the only thing. So this is the condition. They are zero. So this much information first we have to do. Number of nodes, number of elements, number of degrees of freedom. Out of that, what are the unknown degrees of freedom? That is also the kinematic indeterminacy. Only 3 are the unknown displacement. Of course, this out of these 3 is whatever we have asked in the problem that is also taken care. Next step, we have to find the stiffness matrix. This is the first step. And of course, natural coordinate, global coordinate, Jacobian, everything it has already taken place. Because I am using straight away the stiffness matrix. The stiffness matrix of elements. Straight away, I will use this one. So first element, there are how many elements are there? 3 elements. For all the 3 elements, I have to write the stiffness matrix. For first element, stiffness matrix, K1E is equal to EI by L cube. EI is 2EI. 2EI by L cube. L is, for the first element, L is 2 meters, 2 cube. That is 2 cube is 8 into 12. Then 6N. 6N means 6 into 2. L is 6 meters. L, element 1 and element 1 for which L is equal to 2 meters. L equals 2 meters. EI is equal to 2EI. So this is 6L, that is 12, then minus 12, then 6L, that's 12. So this is also 12, minus 12, 12. Then 4L squared. L squared is 2 square, 2 squared is 4. 4 into 4, 16, then minus 6L, that is 12, 2L squared, that is 8. This is minus 12, 8. Then 12. Minus 6L, that is 12, minus 12. Then 4L squared, 16. This is the stiffness matrix of the first element. Or you can simplify this for that. You will get EI by 4, or the 4 I will take it inside, or this will be 4, here it will be 3, 12 by 4, 12 by 4, minus 12 by 4, then 12 by 4, 3, 3, minus 3, 3. Then 16 by 4, it is 4. Then minus 3, this is 2, minus 3, 2. Then this will be 3, minus 3, minus 3, 4. So this is that simplified one. I want this EI to be kept as common factor. So the degrees of freedom, here it is 1, 2, 3, 4. 1, 2, 3, 4. 1, 1, 2, 3, 4 are the degrees of freedom, nodal degrees of freedom for the element 1. Likewise, for the element 2, again for the element 2, L is equal to 1 meter. So it is not 2 meters, L is equal to 1 meter. So therefore, K2 V is equal to EI by L cube, that is EI by 1 cube. 1 cube is 1 itself, EI into this 12 minus 6, not minus, plus 6L, 6 into L is 1, 6, and minus 12, and 6L, 6, so this is 6, minus 12, 6. Then 4L squared, 4 into 1 squared is 4, minus 6L, it is minus 6, then 2L squared, 2, it is minus 6, 2, and this is 12, minus 6L, that is minus 6, minus 6, 4L squared is 4. So the degrees of freedom for element 2, 3, 4, 5, 6. 3, 4, 5, 6. Same thing what you have done in stress analysis, same thing here also, that nodal degrees of freedom you can mention. Then element 3, so for element 3, L is equal to 1 meter and EI because EI itself. Only here EI is equal to 2EI. That's why we just simplified this so that only EI will come in. Then finally I can substitute the value of EI. E and I is constant, it is given. So that I substituted the end. So K3, therefore, element stiffness matrix K3. That's all, only this equation you have to remember what I have derived for the B problems. Whatever the stiffness matrix you have to remember. So K3 is EI by L cube, EI by 1 cube, so that is EI itself, and the same elements 12, 6, minus 12, 6, because L is same. This also will be same. Stiffness matrix for elements 2 and 3 are same. Minus 6, 2, minus 12, minus 6, 12, minus 6, 6, 2, minus 6, and 4. So the degrees of freedom for element 3 are 5, 6, 7, 8. 5, 6, 7, 8. 5, 6, 7, 8. This you have to do carefully. You have to write the element stiffness matrix. So the first step is very important. Wherever there is a change in the load, as well as change in if there is a concentrated load or moment. A moment is given, there also you have to select a node. You have to select additional loads at the points where load is different loads are there other than surface loads. For surface loads, you can find the equivalent joint loads easily. That you can remember. Right? That also you can do in the first step itself, equivalent joint loads. So with that also we will do it. And now I will do it here. So the element of loads are the element nodal loads. Element nodal loads. So P for the entire, because it is in the global coordinates. So for whenever you have a surface uniform surface UDL of intensity W, then the equivalent loads will be like that in the direction of the load. This man is L and this is WL by 2. This will be WL by 2. Then this moment, it will be acting in the clockwise direction like this. Clockwise means it is like this. That is WL squared by 12. Here it is anti-clockwise like that. So it is WL squared by 12. So this you can remember, right? Whenever there is a UDL, say uniformly distributed load, the equivalent concentrated loads are given by lambda. Because load direction is down, which we take as negative. Similarly, here anti-clockwise movements we take as positive, clockwise movements negative. Whereas in the classical approach, we took the other way for movement. Clockwise movement we were taking positive, but here we take the other way, anti-clockwise positive this. So with this, so at nodal degree of freedom 1, 2, 3, 4, 5, 6, 7, 8. Now 8 degrees of freedom transpose the nodal loads. At 1, you have WL by 2. WL by 2 means it is 24 into 2 divided by 2. It is 24, that is minus 24, because it is down. Similarly, this is WL squared by 12. WL squared by 12 means 24 into 2 squared by 12, that is 2 squared 4 into 2, 8. 8, it is in the clockwise direction, so it is negative, minus 8. Then third degree of freedom, again it is minus 24, because it is WL by 2. This is anti-clockwise moment, so it is plus 8. And at fifth, we have concentrated load given exactly corresponding to these degrees of freedom. That's what I showed. Whenever the concentrated load or moment is given on the member, you select a node there and express that degree of freedom there, so that we take care. So since it is acting down, we take it as negative. That you have to remember, all concentrated loads acting up positive, and all moments in the anti-clockwise direction positive. If clockwise moment is given, you take it as moment, negative. And 6, no load, 7, no load, 8, load. This also is a formula in the beginning itself, first step. Then we have nodal load vector, nodal degrees of freedom, and what are the unknown degree of freedom, and element stiffness matrix. This much you have generated. Next, you can find out the global stiffness matrix or structure stiffness matrix. K. For the entire structure, you can generate a stiffness matrix. For the entire structure, that is 8 by 8 matrix, you have to generate. That is 1, 2, 3, 4, 5, 6, 7. For all the 8 degrees of freedom, whatever you got, you have to generate. 7, 8. So problems may be set if there are more number of kinematic indeterminacy. Then they may ask you to generate only global stiffness matrix and stop the work. Because for the further solution process, they may not give it if they give more number of degrees of freedom in the problem. So this you have to generate. This is a very simple process of generating the matrix. So for first element, it is 1, 1. You have to see in this. I have numbered here degrees of freedom. 1, 1, here it is 3. There is no other 1, 1, it is only 3. that 3 and write it. Similarly, next will be 1, 2. 1, 2, 3. No other way, no other point you have below. Now you have the coefficient that only 2 you can write. And of course, EI is common. I have taken outside. If they are different, try to have a common factor here and adjust the inside coefficient. You can add easily. Then 1, 3, 1, 3, it is minus 3. No other thing, it is only minus 3. Like that, you can generate the entire stiffness matrix. All the 8 by 8, 64 elements you can generate it. And stop. If they ask in the problem, generate global stiffness matrix, you can generate it in this fashion. Next, we take reduced stiffness matrix. Reduced stiffness matrix. That is called KD. That is corresponding to unknown displacements. That is corresponding to these unknown displacements, which is corresponding to kinematic indeterminacy, Q4, Q5, Q6. Only corresponding to this KD, which is a 3 by 3 matrix, corresponding to displacements 3, 5, 6. 3, 5, 6. Only corresponding to these unknown displacements, I will calculate it. So the remaining thing, I don't want. Because here also, when once you generate this, you take out only the element corresponding to 3, 5, 6. Like that, 5, 3, 5, 5, 5, 6. You can choose and do it. Remaining things you can leave it. Because here displacement is 0, you can leave this row and leave this column. Because Q1 is 0, Q2 is also 0, Q2 row, Q2 column, you can leave it. Like that, only corresponding to unknown things, you can select it. Yes, I have taken only reduced stiffness matrix, this I have left. So 3, 3, 3, 3, here 3, 3, EI, I will take it here. In all these things, here is common. Then 3, 3, it is 3. Then here it is 12, 12 plus 3, 15, 15. Then 3, 5, 3, 5, here you don't have, here 3, 5, minus 12, then here you don't have, it is minus 12. Then 3, 6, here you don't have, 3 is there, but 6 is not there. Here 3, 6 is there, it is 6. Here you don't have, it is 6. Then it is minus 12, 6. That you can cross check. 5, 3. 5, 3 you don't have here. 5, 3 is minus 12. Here you don't have, it is minus 12. Then 5, 5. 5, 5 is 12. 5, 5 is 12. 12 plus 12, 24. Then 5, 6. Here you don't have. Here it is minus 6. Here it is plus 6. Minus 6 plus 6, it is 0. So here also it has to be 0. You cross check now. 6, 3. 6, 3. It is 6. 6, 3 you don't have, it is 6. Then 6, 5. You don't have. 6, 5 minus 6. 6, 5 plus 6, 0. Then 6, 6. 6, 6, 4. 6, 6, 4, 8. This is the reduced stiffness matrix corresponding to unknown displacements which you have selected. This is an important step whenever you have to determine the displacements. So if you ask only generate the global stiffness matrix, you can stop here. Otherwise, you to find the displacement, go further, take reduced displacement matrix corresponding to that, leaving all the constraints. That is, I told you here, Q1, Q2 and all 0, the constraints can leave it, remaining things correspond to parametric frequency. Then you take the reduced load matrix, reduced element load matrix, element load vector. Here I have generated for the structure, nodal load vector. All the nodal loads, because all the loads has to be only at the nodal points. If there is a surface load, find the equivalent nodal load that I have told. If it is UDL, find the equivalent loads like this. If it is triangular load, you can take it. But if it is concentrated load or moment, you select a node. That is very, very, very important. Whenever concentrated load or moment is given on a member, you select a node there. If there is already a node, forget it. Otherwise, you have to impose a node and it improves the element order, whether it is superparametric or subparametric, like that. So here, PD corresponding to only 3, 5, 6. You have to take it. That is 3 corresponding to 3, it is 24, corresponding to 5, 50. 6, it is 0. So you have to take nodes as, reduce nodes as minus 24 and minus 15 and 6 is 0. Minus 24 minus 15, 0. Then you can use the global or structure equation. KD into D unknown displacement is equal to PD. You solve it, you get the displacement. That's the law of system. So that completes the problem. So finally, we have a system equation. Here Q is the unknown displacement. So that is therefore KD, it is DI into 15 minus 10, 6 minus 12, 6, 24, 0, 0, 8 into minus 24 minus 15, 0. Sorry. Into Q is your Q3, Q4, Q5. They are the known. It's Q3, Q5, Q6. Yeah. Also Q4, Q5, Q6. Sorry, I have generated because unknown displacements are Q4, Q5, Q6. It is not 3. It is 4, 5, 6. So 4, 4 I have to take. 4, 4 means it is 4, 4, 4. Here 4, 8. So instead of 50, you have here 4, 4, 8. Then 4, 5, 4, 6. 4, 5, you don't have. 4, 5 minus 6. 4 minus 6 only. Then 4, 6, nothing. 4, 6, 2. Here you don't have, it's 2. then phi 4, you don't have here phi 4 minus 6 automatically. Then phi 5 okay, phi 6 okay. Then 6 4, you have here 2, here you don't have, here it has to be. That much correction. Immediately you do mistake like that, you can rectify it without any problem. So that is 4, 5, 6 are the unknowns. Here it is Q3, Q4, Q5, Q6. They are the unknown displacements which we have to determine. That you now already have selected is equal to PD. PD is minus 24, 56. Now, this is the equation. Either now we can invert this matrix and find Q4, Q5, Q6, or we can solve the equation. So you can say 15 Q4 minus 12 Q5, 6 Q6 is equal to, this I will take the third side, it will be minus 24 by EI. First equation, second equation, minus 12 Q4 plus 24 Q5 is equal to, and 0 into Q6, 0 is equal to minus 50 by EI. EI I will take it third side. Then 6 Q4, then 0 plus 8 Q6 is equal to 0. So second equation, third equation. So these three equations you can solve, or you can invert this matrix and find out. So this, after solution, you will get what is the thing which is required. That is Q4, Q5, Q6. I'll give it. I have result, you can verify. So you will get Q4, Q5, Q6. You will get it is equal to minus 0.201875. This is radians. Because Q4 is the moment in the problem, whatever we got here. This is Q4 moment which we have to, that is rotation there. This is Q3, first node, second node. So moment, that is rotation, it is in radians. Then anti-clockwise, it is negative, so that means it is in the clockwise direction. That's all that you can say. Then Q5 is minus 0.005677, so many meters. Then 0.30469 radians. This is after substituting for EI, and this is after substituting for EI. EI value, you take it as E is, I have it out, E is equal to 200 GPa, that is 200 into 10 to the power of 9 Newton per meter square, converted it into kilonewtons. So divide by 10 cube, I is given as 2 into 10 to the power of minus 6. So this, it will be 10 to the power of 6, this 10 to the power of 6, it will cancel. So you will get here as 400. So substituting that here as 400, you will get these values. So you can simplify, do it. Here, this is what they have asked in the problem. Find the displacements under the concentrated load. That is corresponds to Q5 and Q6. This is deflection, this is slope, radiance. So this much exercise. So I have covered all the things. Suppose if you want to determine the moments at the ends for drawing Pentygoid diagram, then you go to these elements individually. For element equation you take it. Each element equation. Here I have taken global KD. So you take only the element equation here. For the element 1, you have to find out what are all the moments and shears if you want to determine. So for this, we know that equation, M equation, shear force equation. In that equation, I have given the relationship between natural coordinate as well as global with respect to global distance. Find out the natural displacement and natural coordinate and substitute in those equations for Z and calculate shear force and moment, and you can get that. Or you can use this equation, element equation, Q K1E into QE is equal to P element loads. You can use that from this. This is known. This is also known. PE corresponding to the global load vector, whatever I given. Select only corresponding element. From that you can find the each of this you have determined. You will get the forces PE for each element X. You can work out. This includes one load as well as load and load corresponding to these unknown displacements KD, both Q, KE and element load that you can just add together and evaluate. Or use the equation for each element separately, moment and shear, compute it. Either way you can do it. I prefer to use the equation since I have given moment and shear equation in terms of Z. To take each element separately, use the relationship between natural and global coordinates, get the point where you have to determine moment and shear. That's all. So with that, you can calculate moment and shear at any point in the beams, as well as at the nodal points. If they give arbitrarily in the problem, determine the slope and deflection, you select a node. That's very, very important. You have to introduce a node at that point and generate like this. So the element will become the superparametric element or subparametric element, depending upon number of increased load or decreased load, rather than from the isoparametric. If you are not selecting any extra load, it will be an isoparametric case. That's all. So with this knowledge, so you can work any problem for any load, UDL, triangular load, concentrated load, or moment, or combination of this, by appropriately selecting new nodes. That's it.